So I've tried a lot of different habits and hobbies to try and improve myself when I was in the self-improvement space. Cold showers, early mornings, journaling, meditation. You can think of it, I've probably tried it, right? And I think the problem that we often face is not only is there so much advice there out on the internet, but we often just don't know whether the advice actually works or not, right? And I think that's the big problem. It's not that there's too much. It's just that we get all this advice and we don't have the tools to evaluate whether that advice actually worked for us, if it actually does work, right? And that's what I want to show in this video, is how we can actually evaluate the changes that we make in our life to see if it's actually effective. Now, just a little bit of background of myself. I'm a chemical engineer. I've taken pretty much every single class you can think of under the sun. But if I were to pick one class, I forget everything else and I only took one class, it would be statistics. And I think everyone should take statistics. And what I'm going to show you in this video is how to apply one concept that I learned in statistics to your daily life. And this concept is called hypothesis testing. So with that, let's get straight into it. Okay, so what is a hypothesis test? A hypothesis test is the way that we test multiple hypotheses and we either reject the hypotheses or we accept or we fail to reject. We don't say accept in statistics, but we fail to reject. And so let me actually show you the setup here. So suppose I give you a coin. Okay, it has two sides. You have heads and you have tails. And I give you this coin and I ask you one simple question. Is the coin fair? You can flip the coin any number of times, however many you want, but in the end of it, you have to decide if the coin is fair. Okay? So hypothesis testing gives us a formal way of actually testing this. So how this works is we're going to create two hypotheses. The first we're going to create is the null, also known as the no difference hypotheses. And the no difference hypothesis means that the coin is fair. In other words, the probability of heads is equal to the probability of tails. Those are the same. The alternative hypothesis is the exact opposite of this. We denote by H sub A. And the alternative hypothesis is that the probability of heads does not equal the probability of tails. So now that I have the two hypotheses here, all I'm going to do is make a appropriate sample size to actually test the hypothesis. And what we're trying to do is create something that looks sort of like a normal distribution. So let's suppose I flip the coin X number of times. I want my distribution of possible outcomes to look something like this. This is the bell curve, where if it was a fair coin, the average would fall around half of the things, so X over 2. Of course, we'll have some tiny chance of getting all heads, even with the fair coin, or some tiny chance of getting all tails with a fair coin. But those are in the tail probabilities. They're not much area under the curve. The area is the kind of the probability here. And you can see that the meat of the area is really closer to the average, which is what we expect for a fair coin. We expect it to somewhere fall around half of it. And it turns out to get this kind of normal sampling distribution, what we need to do is get at least a sample size of 30 or more. So X must be 30 or more. So I'm going to flip this coin 30 times. We can always do more, of course, but let's just say we flip the coin 30 times. You're going to record how many heads you get. You're going to record how many tails you get. And now the question is, you flipped it this many coins. If the coin were actually fair, what's the probability that you would get this result? Or, in other words, something more extreme. This is called the p-value. And so let me show you what that looks like in practice. So I'll give you two cases here. So we'll give case 1 and case 2. So case 1, you flip it 30 times and you get 20 heads and 10 tails. Okay, if it was, we expect it to be 15-15, but we got 20 heads and 10 tails. So the question is, and I'll draw my normal distribution here again. Looks something like this. Let's just say this is the number of heads. And this is the relative proportion. Expect our mean for a fair coin to be 15. And so what we're looking for is the probability that we would get this outcome or a more extreme outcome if the coin were fair. So let's just say this is 20. This is 10. So in other words, the p-value here is going to be equal to the probability that we have greater than or equal to 20 heads, or the probability that we're greater than or equal to 20 tails. So in other words, we're looking for the area at the end of these curves. And this actually, there's some tables that you can use to look this up. I'm not going to go too much in detail. You can always ask AI to actually calculate what the p-value is here. But this actually turns out to be 0.098, roughly speaking. Or in other words, there's a 9.8% chance that I would get 20 heads and 10 tails, given that the coin is fair. So the question is that low enough for us to reject the null hypothesis? Is that low enough to say that, oh, this coin is definitely unfair? Well, no. Basically, every time I flip the coin 30 times, 10% of those times, I'm going to get 20 heads and 10 tails, or something more extreme. So it's likely, it is possible that we could have a fair coin still. So in this case, what we do is we fail to reject the null. We don't say we accept the alternative, we always say we fail to reject the null. That's just the statistics language, but for all intents and purposes, we are going forward with the assumption that the coin is fair. Now let's look at case 2 here. So case 2, I have 28 heads and 2 tails. So in my normal distribution, centered around 15, here's 28, and here is 2. You can see that the areas are much smaller compared to the example above. If I were to compute my p-value, which again is the probability that I have greater than or equal to 28 heads, or the probability I have greater than or equal to 28 tails, this actually becomes 0.000000698, otherwise known as 0.0000698% chance that if I had a fair coin, I'd get 28 heads and 2 tails. Now, this is basically in the realm of impossibility. It's not likely that we would get this outcome. So in this case, we reject the null hypothesis and go forward with the assumption that the coin is unfair. Now, this was a pretty long-winded explanation here, but the point that I'm trying to make here is that we can do this exact same testing with real life practices or real life changes that we're making on ourselves. So let's actually take an example here. This is our real life example. So suppose I am trying a new morning routine. I heard waking up at 5 a.m. is going to change your life. Absolutely. So this is the habit we're trying to change, right? Okay, I have a routine. It's a new routine, old routine. So the question is, Does it make a difference? Does it have an impact on the actual probability? So this is again a form of hypothesis testing. In particular, for my stats nerds in the audience, this is a paired. What we're going to do is we're going to do a paired t-test. So it's before and after comparisons. So all we're going to do is we're going to pick a measurement. As long as it's consistent and it's numeric, it's measurable, right? It's not just like a vibe check, right? So we have a couple options here. We could rate our energy at the end of the day or after work. So we can rate our energy every day at 5 p.m. when you get home from work. We could count how productive we were, so count number of tasks complete. Of course, assuming that all the tasks are roughly around the same size. We could count how long it takes you to get out of bed or complete your morning routine. There's a number of different things we could do. Whatever it is, pick one, make sure it's consistent. Don't switch. Make sure you define how you're going to rate this, right? Then, again, we're going to do our sample size here. So let's do 30 days using the old routine, and then we're going to do 30 days using the new routine. So you do day 1 of the old routine, waking up whenever you want. Let's just say your energy is around a 6, I don't know. And then the next day, you had a really good day, so you had a 10. The next day was around an 8, and then so on and so forth. And then you do the same thing with the new one. You do day 1 with the new routine, say it's a 7, day 2, it's a 9, day 3, it's also a 9, etc., etc. So I got it 30 days, log the metric. It's my control data, in other words. And then I have my experimental data for the next 30 days, or before and after. And now that I have 2 sets of 30 data points, I could find the difference between each one of those and find the average and standard deviation for those. Now that you have the standard deviation, if you know the math, you can do the math here, or you can plug those averages and standard deviations into AI or some online tool and ask, what is the p-value? And then you'll determine, based on the p-value, did the change actually have an impact? So let's suppose I did this, and then my p-value was, I don't know, just for sakes of argument here, let's just say it was 12%. So again, remember, I should have defined this earlier, our null hypothesis and our alternative hypothesis. Null is that the old routine equals the new routine. Or in this case, I shouldn't say probability. The old equals new. Alternative is old does not equal new. So assuming that the null is true, assuming that old and new are equal, I have a 12% chance of getting the results that I got. I would reject the null. If it was like that other example where we have a 0.00 something approximately close to 0%, we reject the null. This threshold that's typically used in statistics is 0.05, basically a 5% chance. If it's below 5, we reject. If it's above 5, we fail to reject. But again, that depends on how much error you're willing to introduce. And that's a whole can of worms that I'm not going to get into. But my point is, now you have a numeric number, a p-value, in essence, that tells you, okay, is this new routine actually doing anything for me? Have I actually changed because of this? Right? And you'll find by doing this that some things may not do anything for you. For example, for me, I found that waking up at a consistent time did do something for me. My p-value is much less than 0.05 versus when I did this for cold showers. Cold showers did nothing for me. When I did the test, I was like, there's no real difference between me taking a warm shower and me doing a cold shower. So why would I sit in a cold shower when I can just have a nice warm shower? So this actually will show you what is actually happening here and are you actually improving? And morning routine is just one example. A new workout program, different study methods, a dietary change, even something low stakes like I don't know, like tracking a compliment after a new haircut. Is this haircut making you more attractive? Like you can figure this out just by doing this small statistical test and seeing if you're actually changing things. Instead of evaluating the change based on your feeling, you now have a process for removing all the noise and your feelings and actually knowing numerically what's actually moving the needle. Anyways, that's it for this video. Hopefully you found some value from this, and I will see you all in the next one.